All right, now I'm going to go to the full screen mode, so I won't be able to see your comments. Okay, guys, welcome back. And so today we're going to do something exciting. I really like this topic, and I hope you'll also enjoy this. So this is kind of a culmination of everything that we have done through the semester. We have discussed the combinational logic, and we have been working with sequential building blocks, right? We looked at the D flip-flop. We did the applications of D flip-flops as registers, as shift registers, and then by adding additional modules to the D flip-flop in the last class, we realized a new type of a flip-flop with additional states that a simple D flip-flop would not offer us, right? And that's the J-K flip-flop. So it's very similar in operation to the SR flip-flop. The only difference is, of course, in the as with the SR flip-flop, we had the memory state, we had the set state, the reset state. Now, but different from the SR flip-flop, this JK flip-flop had an additional state, a useful state, right? In the SR flip-flop, we had the forbidden state. In the JK flip-flop, we actually had what is called the toggle state, which was actually very useful. It was a determinate state. That means I'm able to actually use it. I know exactly what happens when I apply when I apply J and K both 1. I know exactly what will happen. As a function of clock, my signal will toggle, and I can use that when I can apply that for different applications as frequency divider, as for example, we have looked at the examples of counters in the last class, a ripple counter and the synchronous counter, right? Okay, so now moving forward, we'll look at other additional applications. Okay, and this is one of the most important application. We'll start with the state machines. Okay, so these are more the advantage of working through the state machine approach is that if you recall, when we were trying to design the synchronous counter, okay, the design itself is not very complicated. However, it was not very intuitive either. You really have to, look into exactly what's happening and then try to come up with that design based on your intuition and logic, right? Now, the state machine approach, when we designed these sequential building blocks or sequential circuits, the state machine approach is more direct, I would say. Okay, just like it's a difference between doing the simplification of functions using the Boolean algebra method versus the K-map method, which is more direct, more compact, more faster, right? So let's look at the state machine approach. Okay, let's look at the design of state machines. And before we actually get started, now let's actually define what do I mean by state. Okay, now as the name suggests, the state machines are basically machines. I can basically say that these are the machines that can exist in multiple states. Okay, but what do I mean by state here, right? Now first let's understand that. What do I mean by state? Now what do you understand by state? We use it all the time, right? Can anybody provide me with what they understand by state? For example, when we apply it to our own daily life, we use it in our daily language, right? When we say, okay, I'm in a good state, I'm in a good state of mind, all right? Or I'm in a happy state, yeah. So when I pertain this definition to, let's say, humans, we talk in terms of emotional states, right? So when I say state, we talk in terms of a state of being, right? So when it pertains to humans, we talk in terms of emotions. And let's say, if I want to list out some of the most important emotions, I would probably list them out as a happy state. That's one emotion. Okay. As a sad state, another emotion. Let's see what else. We have angry state. Any other examples that you can provide? Just the states that we find ourselves in daily life, right? So happy state, sad state, angry state. What else? Any additional states that you find yourself in? Again, scared, okay. Again, because I'm in the full screen mode, I won't be able to see your text messages. So if you can speak up, I'd appreciate that.
Calm state.
Calm state, yeah. All right. So these are some of the most common states, right? Of course, the list goes on. Actually, as a matter of fact, there was a CNN study that was done, I think, a couple of years back, and they've scientifically proven that humans can exist in about 26 different states. Okay, so if you just type it in Google, a CNN study and then human states, you should be able to get that article. It's a very interesting article, and you can actually have these the the faces corresponding to each state. Okay, you have a state, you have a happy face; sad state, you have a sad face, and so on. Okay, so it's actually a very interesting study. Okay, so let's say you have 5 states, right? Now, if I want to represent a human being, of course, representing a human being is not very easy. Human beings are very complex individuals, right? So if I want to, if I want to simplify that and then put that, if I want to get a snapshot of how a human being exists, okay, then I can represent that with the aid of what is called a state diagram. Okay. Again, it's an accepted fact that we human beings can exist in multiple states, right? That's what makes us special. That's what makes us different from an inanimate object, right? And the other accepted fact is that, again, we exist typically, most human beings, the vast majority of the human beings, we exist in one state at a given instant of time. All right, we only exist in one state. It's not like we continue existing in that same state. We do change states. So what facilitates the changing the state? It's the time, right? So somehow we have the sense of time, and it is the time that facilitates the changing in states, or or if I want to put it in more technical terms, the state transitions. So I go from one state to the next, and the transition is facilitated by time, right? By the movement of time. That's one thing. The second observation is, of course, we only have one. We are only in one state at a time. And what is the determining factor that determines the changing state? Let me see if I can get an answer from you guys. Okay. So let me put the information down. Okay, let me not do this. We have happy state. So we are working at this time with 5 states, of course. Now what I'm saying is that at a given time, these are the observations, at a given time or a given instance, a human being exists in only one state. We exist in only one state, whether it's happy state, whether it's sad state. Of course, there are some people who may exist in multiple states at a given instance, but for the vast majority of us, we only exist in one state at a given time. Then we do change states, or we do undergo changing in states or change in states. And what facilitates that? It's the time. It's the time, the movement of time takes me to one from, or facilitates those state transitions. Of course, if time was frozen, then I will always be frozen in that particular state. That's kind of obvious. Third, okay, that's the third observation. Just again looking at different observations, just as considering human beings as state machines, if you will. Okay, we are capable of existing multiple states, and these are some observations corresponding to them. Now, what is that determines those state changes? Let me put it this way: I'm in a particular state, right? At the next moment, what state I will be in? What is that determines that? Can I get any comments from the class? Okay. Yes. External influences. Yes, that's a very important. Is that the only one? Are there any other factors that would determine that those state transitions, if you will?
Memories?
Our thoughts.
Sorry? Memory? Yeah, that's a good point. What else?
I said thoughts.
Thoughts. Okay. Thoughts. Okay. Can I say at a given instance, external influences is one aspect, and also my being, right? Let's say I'm in a calm state. Okay. And, something happens. I'm in a very calm state and I see a snake. Okay, that's an external influence, right? My next state is determined by both my present state, which is I'm in a calm state. That means my nerves are cool. I'm in a cool state. I see a snake. Most likely, of course, I may react, but most likely I may still be. Well, let me put it this way. Most likely, I'll be reacting in a more rational way. Does it make sense? Versus if I'm in the scared state, okay, I'm already nervous, I'm scared, and the same external influence happens. Let's say I see the snake. Most likely, I will be reacting in a completely different way. Right? Does it make sense? So what I'm trying to get to is the next state that I will transition to is dependent both on my present state of being as well as the external influence. So external influence and the present state of being. So I need to know what state I am in. Present state of being. So how I react for an external influence depends on what state I am in at that instant of time. Okay. All right. So these are the three facts that I've gathered. Okay. And if I want to provide a snapshot of that individual who exists in 5 states, just as a simple example, I can provide that information using the aid of a state diagram. Okay. So let's actually start drawing that. Okay. Again, I have happy, sad, angry, scared, and calm state, right? Okay, so I remember that. I have 5 states. So I will represent each state with a circle with something descriptive, yeah? So let's say happy state, you know how that is. I have a smiley face. That's the happy state, okay? Then I have a sad state. That's easy. All right. And the third state was angry state. Okay, that's my angry state. Fourth state was, what was that? Fourth state. I had angry, happy, angry, sad, angry, and then we had the scared. Right? That's the scared state. And then finally we have the calm state. I don't know how to draw calm. Let's see. All right. I hope that's representative of calmness. Okay. All right. So I have 5 states. I put down the information. Now I need to work with the state transitions. Again, a given state plus the external influence. Well, in a way, I can call my external influence as an input, right? Those are my inputs that are acting on me. Okay, so I'll consider them as inputs. Those are the inputs that are acting on me. Along with the present state, determines the next state transition. Those state transitions are facilitated by the time. We have a sense of time. So let's say I'm in a happy state. So the way I will draw this state diagram, these are the rules I will use. Okay. So I would go to each state. So let's say this is my happy state, and I would look at all possible external influences that are occurring on me on this particular given state. Okay. All possible external influence. And then I will look at all possible state transitions that are occurring because of those external influences when I'm in this state. For example, let's say I'm in this state and an input and a happy input occurs. Okay. If a happy input occurs when I'm in this state, I draw the state transitions using these kind of arrows. Okay. If a happy input occurs, I remain in the same state. I'm in a happy state. A happy input occurs, or a happy external influence happens. I read as happy news, something like that. I remain in the same state. So I basically feed back into the same state. So even with the progression of time, I'm going back, I remain in the same state. So that's kind of understandable, right? I'm in the happy state. What takes me to the angry state? What kind of an external influence would take me to the angry state? Again, that could be some kind of bad news or something. Again, an external influence. When I'm in the happy state, that takes me to the bad state. Again, the idea is I show the state transitions through these arrows, and I place my inputs on those arrows to signify that this is the input that occurred, and this input when it occurred when I'm in this particular state transitions me from this state to the next state in the future. Okay, so in the future state, so if I'm in this particular state in the present, then if this particular input happens when I'm in this state, my future state is going to be the sad state. Okay. Now again, I'm in the happy state, and let's say I keep getting bothered or pestered. Again, that's an external influence, some kind of an input that is occurring on me when I'm in the happy state, and that transitions me to the angry state. Okay, and likewise, I can draw these kind of state transitions. So once I'm done with one state, I move on to the next state. Okay, let's say I move on to the happy state. Again, if I'm in the happy state, let's say I have a happy input happen. I'm in the sad state. Let's say I have a happy input happening. Okay, so my future state is going to be the happy state. So I have sad state, a happy input happens, or happy influence happens. That takes me back to the happy state. Okay, and so the state diagram, the basic function of the state diagram, this is completed, of course, when I do this exercise for each of the state. So I look at all external influences that are occurring on each state and draw the state transitions from that state to the next state. When I complete this exercise for each state, I'm done with the state diagram. So that's my state diagram. And what does it do? It basically provides me with a snapshot of that individual, of that machine, of that state machine, how that machine operates, how that machine transitions from one state to the other. Okay. In this case, of course, we are still considering the example or the analogy of a human being as a state machine. Okay. So far in our discussions of design of combinational circuits, we have really looked at passive instruments, passive circuits that only exist in one state. Okay. Now we are going to actually design machines that can exist in multiple states, and that is more functional. Okay. Ultimately, if you think about this, your computing device is a state machine that can exist in multiple states. If you can think of a simpler example, another example of a state machine would be, let's say, a washing machine. Right? All of you use washing machines. You have worked with this, and you know that's a machine that can exist in multiple states. What are the states associated with a washing machine? Again, you have the load state. You can call that a state. We have the rinse cycle. We can think about that in terms of a state. you have the spin cycle, you have the wash cycle. So all of these cycles are, now you can start thinking about them as different states associated with that particular machine. Now, the good thing is, when you're operating the washing machine, all you have to do is load clothes, put the detergent, and turn it on. Set your cycle to whatever cycle you want to set, and hit the start button, and it will automatically transition from one state to the other, right? It automatically goes from the washing cycle to the rinse cycle to the spin cycle to the, and so on and so forth. So it automatically goes through that cycles. So with the aid of a state machine, I can design these circuits or instruments that can actually exist in multiple states, and that can be programmed so that it can actually switch from one state to the other without an external with minimal external supervision, if you will. Okay, so that's the idea. Now, other examples of state machines, your a traffic light controller could be a state machine. Would be another example of a state machine. Again, you have multiple examples of this sort, but I'm just trying to give you some kind of connection here, so that you can actually make that connection between these kind of machines. Okay. All right. So that was the example of the. Again, I can draw these. So if I want to complete this, I have different external influences, and I have to basically complete this diagram so that I exhaust all the external influences on each state and draw the state transitions accordingly. Okay, so something that takes me back here, takes me back from here to here, and so on and so forth. Okay, now the idea is we want to translate that information to designing a actual machine that can exist in multiple states. Again, as with the rest of the classes we had, we are trying to design a digital system. Okay, a digital system as in that can recognize ones and zeros, and we want to design one that can exist in multiple states. Okay, and how do we do that? All right, now as with any digital system, the only things that a digital system can recognize are these ones and zeros, right? Voltages, ones and zeros. So if I want to have states for a particular state machine consisting of, let's say, n different states, now each state, for human beings, we have this internal encoding mechanism through chemicals and so on. So we know if you are in a happy state, we know we are happy, we are self-aware, right? Versus when we are in the sad state, we know we are sad because of all the chemicals or neurotransmitters that are being released in our system. Now, if I want to translate that analogy to state machines, these machines are machines, they are not self-aware, right? Again, the intelligence behind the design is again you as an engineer, right? So if I want to design a state machine that can exist in multiple states, let's say these 5 states, okay, I need to encode each state with a digital code, right? So that once as the state machine goes from one state to the next, depending on that digital code, we can know exactly which state that machine is in at that particular instance of time. I hope that makes sense. So everything has to be encoded in terms of zeros and ones. So if I want to encode the state information itself, then what I would do here, for example, would be I would encode let's say the happy state. If I want to make a state machine out of this, a happy state with a unique code. I have 5 states here. Each state has to be encoded with a unique code. So happy state, let's say I encode it with a code 0. So by the way, how many bits should I use to encode my states in this example where I have 5 states? How many minimum number of bits I should use? Binary bits should I use? So that I can have a unique code. Yes. So that I can have unique code for each state. So I can encode my happy state with 0, 0, 0. Let's say a sad state with 0, 0, 1. Angry state with 0, 1, 0, scared state with 0, 1, 1, and calm state with 1, 0, 0. So these are the unique codes that are being used to encode each of my state. Okay, and I encode them in what are called state variables. Let's say I use 3 state variables. So these are my state variables. Okay, and at any given instant of time, those variables are going to change. As time progresses, those variables are going to change, signifying that I'm moving from one state to the next. Okay, so that's something that you need to keep in mind. Now again, going back to the human example, right, we have developed the sense of time through all these chemical changes that are happening in my brain, right? Now, what about machines? How do I incorporate the sense of time or timing into my machine? What should I do? Because obviously, if I design a combinational circuit, that's not really progressing in time. It's always in a single state. But if I want to progress a machine through different states, which happens through progression in time, how can I incorporate the timing information into my state machine? Any insights on that?
Use a clock.
I can use the clock, absolutely. Clock. So in this case, for a state machine, for an actual digital system, I can use clock for timing, to incorporate the sense of time into my machine. So the clock progresses as the clock signal progresses. My machine is progressing through time. Okay, so that's the idea. All right. So now, if I want with that information, again, to summarize, in terms of designing a state machine, a digital system as a state machine, it is the clock that facilitates state transitions, facilitate movement of time, facilitate movement of time or state transitions, right? And then you have the inputs, whatever the inputs are that are occurring, along with plus the present state itself. Now, present state, what do I mean by present state? My every state now is encoded as a unique binary code, right? So the inputs combined with the present state would decide or determine the state transitions or the next state, right? Okay, so these are the two important characteristics of state machines. It is the clock that facilitates state transitions or movement in time, advancing the time for the machine, and it is the inputs and the present state combined. So the inputs have to be combined with the present state, which are again basically unique binary codes, to produce the next state, right? Depending on how you want to configure your state machine. All right, so that's very good. Now, with that information, let's actually look at a generic state machine, all right, based on this information. So what I'm doing here is basically trying to build this state machine. Again, I'm looking at the level 0 block, all right. Now again, some inputs are acting on this block. I have again multiple inputs. I want to generalize this as much as possible. So these are the inputs acting on this block. And this particular block takes in the inputs along with the present state. Okay. Now again, the present state is encoded in terms of the state variables A, B, and C. Let's say in this case, so these are the inputs. These are the present state A, B, and C. present state. The values of A, B, and C would tell me what state I am in at that particular instance of time. So that's the idea. So that's my present state. Okay. All right. And that determines, so this inputs, so these are the inputs along with the present state combined in a certain way. I don't know what way we're going to combine them, but combined in a certain way would tell me what my next state should be. So these are the outputs. Of course, I have some outputs here that I may produce. And it also produces what state I should be in the next state, or what is my next state going to be based on my present state values and the inputs applied. Okay. If I want to make this progress in time, I have to introduce the concept of clock, right? Because once I do this, once I produce my next state, I have to advance in time so that my next state or my previous next state becomes my present state, right? At a given instant of time, once I've frozen the time, I combine the inputs along with the present state to produce my next state, right? My values in the state variables changes, and in the future, that next state becomes the present state, right? So if I want to advance in time, so what I will do is I will use these flip-flops that are synchronized with the clock, so I have 3 flip-flops here. Okay, for simplicity, I will use D flip-flops, but I can use any flip-flop for that matter. Okay, so let's say this is DA, DB. So this is how I introduce the concept of timing, the clock, because as we discussed, it is the clock that facilitates the clock transition. So I have to somehow introduce the concept of timing into my state diagram or state machine, right? DC. So again, as you can see, the number of flip-flops I would use depends on how many state variables I have in my design. Okay, so that's my next state being fed to these flip-flops, and I assume that of course I'm applying the clock, but this clock is internally applied for, even though I just show it for DC, the same clock, the master clock, is also internally applied for DB and DA. So you can just although I don't show it explicitly there, you can assume that it's there. Okay, that's my QC, QB, QA. So now once I interconnect this in this manner, so QC going to C, QB going to B, and QA going to A. Now I have designed a state machine, a generic state machine consisting of 3 state variables. Or again, you can, depending on how many state variables, you can increase them. For now, I'm just showing for 3. Okay, and the way I have drawn it, my inputs combined with the present state at any given instant of time, producing the output, producing what my next state should be. Okay, now as this clock transitions, the next clock pulse, this input or the next state becomes my present state, right? And then it combines with the inputs. The inputs can change at that time, producing the next state. Okay, and again with the next clock transition, though that next state becomes the present state through this feedback, combines with the inputs, and so on and so forth. Now I have a machine that can transition in time, that can actually move forward in time, switching from one state to the other depending on my inputs and the present state. So the generic block diagram of a state machine itself is actually pretty simple. You just have 2 blocks. Okay, one is this block. It combines the inputs with this present state, producing the next state and the outputs. And of course, you have the flip-flops. Again, you don't have to do anything in the design of the flip-flops, right? You have the flip-flops, they are there. You just have to make that feedback connection. So the design, in terms of design itself, all you have to do comes back to the design of this block. What kind of a design is this? What is that? What kind of a logical block you think that will be in this case? All this block is doing is taking the inputs, whatever the inputs are being applied, combining with these values that are present on the state variables, some binary values on the state variables, producing the outputs. In other words, this is a simple combinational block. So the design aspect comes back to just designing this combinational block. So whatever you have learned in terms of the design of a combinational logic still applies here. So we still have to use those principles, the K-map approaches and so on to get to the simplest functions. So ultimately it boils down to the design of this block. Okay. So once you are through this stage, the design itself is pretty straightforward. The real the real part where you really have to think through this occurs in the initial stages, where you have to identify the inputs. You have to identify how many states should I have, what those states should be, how would you define those states, okay, and then coming up with a state diagram, and then we basically follow through a sequence of well-defined steps, just like how you did in the K-map approach, right? In the design of combinational circuits, we went through a sequence of steps, identify the most important steps where you really have to think through occur in the beginning, where you had to come up with a level 0 design, where you have to identify the inputs to the block, the outputs from the block, and the functionality of the block. Okay, once that is determined, everything else is pretty simple. You just have to put that information down in the form of a truth table or a K-map. Once you have the K-map, it's just a matter of combining, getting the simplified function, following some rules, and you get it, right? In exactly the same way, here we have to follow through a sequence of steps. Okay, so let me take a pause and see if you have any questions until this point. If you can speak up, I would appreciate that. Okay, so no questions, then let's actually move on now. So that's the genetic diagram, and I would really emphasize that you understand this, okay? And this is very important, because once you derive your state equations and functions, you need to know how to combine them, how to actually realize that circuit. And I will always go back to my generic state machine block diagram for that purpose. Okay, so let's move on. So now let me actually summarize the steps that we have to take in the design of sequential circuits, state machines that can exist in multiple states. Okay, so when you're given a problem statement, this is what the approach you should be taking. Given a problem statement, just like what we have done before, the first step is identify the inputs to the system. Identify, of course, you need to understand what the problem statement states, identify the inputs and the outputs. What are those inputs and the outputs? Identify, in this case, because you're designing a state machine, you need to also identify the states. Identify what constitutes the state, a state for the machine. What constitutes a state for the machine? So once you do that, you will know how many states should the machine have. Should the machine have? Once you know how many states the machine has, you will know how many state variables should I have. Okay. So inputs, outputs, identify what constitutes a state for the machine, Then once you know that, design how many states should the machine have based on the problem statement. And then once you know the number of states, how many state variables should I have, so that I can have unique codes associated with each state identified state. Okay. Then this third step, once you have done this part, is translate all that information into a state diagram. Okay, what is a state diagram? It's more like a snapshot that we just discussed, right? You basically have all the states listed, and then you're looking at the state transitions. So for a lay person, if he just comes and looks at the state machine or the state diagram, he would understand exactly what that machine functions as. Okay, so draw the state diagram, and once you have this, once these three steps are done, the rest of these three steps are basically very mechanical in nature. You don't have to really think much. Once you know the technique, it's pretty straightforward, standard. Okay, state diagram, you basically translate that information of the state diagram to what is called a state table, and from the state table, you'll basically realize the circuit. Again, remember that, realize the circuit. Ultimately, what it boils down to is you're designing the entire problem statement. The solution boils down to designing of the combinational block. Okay. Now, once you know how many state variables you have identified, the number of flip-flops, you will know exactly how many number of flip-flops you need to use. Number of flip-flops to be used, because the flip-flops are the ones that store the state information. Okay. Number of flip-flops to be used equal to number of state variables. We have just seen that. So this is the approach that we will take. Okay, 5 steps. The most important steps are the 1, 2, and 3. The rest of the steps, once you remember the block diagram of a state machine, and the rest of the steps are basically pretty straightforward. Okay, as you will see when we actually do some examples. All right. So with that, let's actually familiarize ourselves, because this is the tricky part. Identifying the inputs, identifying what constitutes a state, that becomes the tricky part. Okay, that's where you really have to think through logically, think through intuitively. And so let's look at some examples for that. All right, let's do this. So let's first try to come up with a state diagram of a D flip-flop. Simple example where I want to come up with a state diagram, want to draw the state diagram of a D flip-flop. So what constitutes the state of a D flip-flop? That's the first thing I need to identify, right? Of course, for the D flip-flop, I have one input, that is my D input. Okay, whatever that is applied to the D, that's my input here. Okay, and what else? So and of course, my output for the D flip-flop is the Q. Okay. Now, what constitutes the state? The state of the flip-flop, or the being of the flip-flop. Again, for the D flip-flop, I can think of the output itself as a state, right? Either the D flip-flop is in a state of 0, where my output is 0, or a state of 1, where my output is 1, right? So the output Q itself constitutes the state. And the state changes depending on what I apply on my D input, because for a D flip-flop, as you remember, my output follows the input with every clock pulse, right? With every active edge, my output simply follows the input. Whatever is applied to input, my output basically follows that value. Okay. All right. So with that information, let me put together as an example. The first example, the state diagram for a D flip-flop. I have two states because the way I've defined what constitutes the state is the value on Q, right? The value on Q is what constitutes the state, where the Q can take two values, 0 and 1. Okay. So here, I can draw that in terms of S0, where my Q is 0, S1, Q is 1, right? In this case, my Q is 0, Q is 1. This is one way of representing the state diagram, where my outputs are represented along with the state itself, because the way I've chosen my state in this particular example, I'm looking at the Q itself to constitute the state of that flip-flop. Okay. All right. Now, the way I will draw that is, again, I go to each individual state. So I'll start with the S0 state. I have only one input, D, right? So either D can be 0 or 1, right? If I'm in this state where my Q is 0, all right, and if an input of D equal to 0 occurs, if I place a value of 0 on my D input, what state transition should I have? Should I remain in the same state? That means in the next clock cycle, would I be remaining in the same state, or would I be transitioning to the next state, or to the different state, to S1 state? If an input of D equal to 0 occurs, for a D flip-flop, again the output follows the input. So if an input of D equal to 0 occurs, I remain in the same state in the next clock transition as well. Does it make sense? Anybody have a
Okay,
question?
and then if D or your input equals 1, you'd hit up to the next state, right?
That is correct, right? Again, this transition, when I represent this in this way, what I mean is, in the next clock transition, if I apply D equal to 0, in the next clock transition, I remain in the same state. Or in other words, in the next active edge, I remain in the same state by this feedback mechanism. That means my future state is the same state. Okay. Now, if I'm in this state, a 0 state, and if an input D equal to 0 occurs, or D equal to 1 occurs, okay, in the next active edge, I would move to the next state, right? D equals to 1 takes me to the next state. Well, I'm sorry, next state as in the Q equal to 1 state, because my output changes, my output follows the input. So in the next active edge, I'll be transitioning to the Q equal to 1 state, or S1 state. Now, I have exhausted all combinations of the input when I'm in this state, right? I only have one input D. And the only two ways that the input can change is D equal to 0 or D equal to 1. So I'm done with this S0 state. Now I move on to S1 state. I'll do the exact same thing there. Let's say I'm in the S1 state, okay? That means my output is Q equal to 1. And if an input of D equal to 1 occurs when I'm in the S1 state, so in the next transition, or what will be my state transition now?
You'd stay in the same spot again.
Sorry?
You'd stay in the same state.
Do I stay in the same state if D equal to 0 occurs when I'm in the S1 state? If a D
equals 0, you'd go to S to the other state.
Yes. If a D equal to 0 occurs, I transition from the S1 state to S0 state, right? Because my output follows the input for a D flip-flop. So with the next active edge, I go from S1 state to S0 state. Okay. Now, if I'm in this state, S1 state, and if an input of D equal to 1 occurs, what would
now
be?
You would stay in the same state.
Now I remain in the same state. That's absolutely right. Because my output follows the input, right? So that my future state remains the same state. So that's it. So that's the state diagram of a D flip-flop. Okay. Now let's see how we are doing on time. Can anybody tell what time is it?
11:53.
Okay, great. Thank you. Okay, so we are here. Now let's look at another example. How about a state diagram for a J-K flip-flop? Okay. Let's look at an example of a for the J-K flip-flop. In this example, what we will do is we'll actually try to implement a J-K flip-flop as a state machine. Okay. All right. Again, so the first thing is identify the inputs. My inputs are, in this case, two inputs, J and K, right? For a J-K flip-flop, I have two inputs, J and K. So I have to identify the inputs. My outputs, I have Q, right? The output of the J-K flip-flop, Q, that's my output. And the state. What constitutes the state? Again, as we have seen for the D flip-flop, in this example,
Would it be 0 and 1 again?
we can do that. Again, the output, the state of being of the output. And the output can remain in 0 or 1 state of the Q value, right? I've identified all of these. So how many state variables should I have? Because I have two states, because Q can be 1 or 0. Twice I have two states that this machine can exist in. Implies I have one state variable, right? Because each state has to be encoded with a unique value, binary code. Two states, I can encode it with 0 and 1. Okay, so that's good. So I've done the first three steps, and now I would like to draw the state diagram for this. All right. So let me now use, so here, okay, fine. Okay, two states. Let me call that as 0 state, where my output is 0. S1 state, which is defined as with my output as 1. Okay, I have two inputs occurring now. Again, just for your remembrance, this is how the characteristic table for a J flip-flop looks. Two inputs J and K. This is what is going to happen in the next active edge. If I apply 0, 0 on J and K, in the next active edge, my Qt plus 1 becomes 0. That's the reset state. 0, 1. I'm sorry, that's not 0. That's the memory state, right? Remember, that's the memory state. So that's whatever was previously there, that continues to remain on Q. 0, 1 is the reset state. 1, 0 is the set state. 1, 1 is the toggle state. So that becomes Q prime of T. So whatever was there before, if I apply J and K as 1, 1, in the next active edge, my output will toggle. Whatever that was there before will get complemented. Right? We have seen that in the last class. And with every clock edge, if I keep my J and K to be constant at 1 and 1, I'll have a square wave produced with half the frequency of the clock. Yes, because for every clock edge, my output toggles. Okay, with that, so that's the characteristic table for a J-K flip-flop. And now let's translate that information into the state diagram here. I have two inputs J and K. So again, as with the previous example, let's say I'm in the state as 0. Okay, and a J and K value of 0, 0 occurs when I'm in this state. What would be my state transition in the next clock transition or in the next active edge, how should my
Would you stay in the
transition?
same spot?
I stay in the same spot because that corresponds to the memory state, right? So I stay in the same spot, same state. So J and K equal to 0, 0 puts me back in the same state. So that's good. If I'm in a 0 state, again, now I need to exhaust all these combinations between the inputs. For a single state, I have to exhaust all these combinations of the inputs. So let's say I'm in this state and an input of 0, 1 occurs. What should be my state transition? What happens? How should I transition between the states now? Should I remain in the same state if 0, 1 occurs, or should I move to the other state in the next clock transition?
Stay in the same state?
Stay in the same state, because this is the state that corresponds to q equal to 0. If 0, 1 occurs when I'm in this state, I remain in the same state because my future value is also, my future state is also q equal to 0. I remain in the same state. All right. I'm in S0 state, 1, 0 occurs on my J and K. My future state, my future output will be 1, which is basically S1 state. So I need to transition to this state with the input JK equal to 1, 0. Okay. And the final input is 1, 1, right? I'm in this state.
Dr. K,
Oh, sorry. I don't know why.
I think the webcam is not working.
Yeah, I see that. Okay. See that now, right? Are you able to see it now?
Yeah, it's good now.
Okay, good. So final input is J and K both 1, 1. I'm in a 0 state. With this input, what should be my state transition? I'm in a 0 state where my Q is 0 because my Q, I've identified Q as my state of being for this particular system. I'm in this state, 1, 1 occurs.
Transition to the other one?
Transition to the other one because I'm toggling, right? So my output is 0. In the next state, if I'm applying 1, 1, my output should toggle, so Q should become 1. So yes. So JK 1, 1 takes me to the next state. It takes me to S1 state here. So I'm done with S0 state. I've looked at all possible combinations of the inputs. I've exhausted all possible combinations of the inputs. I'm done with S0 state. Now I can move on to S1 state and do the exact same process, same routine. Okay. All right. So I'm in the S1 state now. The input 0, 0 occurs. When I'm in S1 state, that corresponds to the memory state. That means in the next clock transition, I remain in the same state. That because J and K equal to 0, 0 constitutes memory. Right. Now I'm in S1 state. The input of 0, 1 occurs. All right. When I'm in S1 state, my output is 1. Now the output has to change to 0. Right. So I have to, because my outputs are, so I have to transition to the next state with 0, 1. Okay. With 1, 0, if I'm in S1 state, input of 1, 0 occurs. The next state should be basically 1, should be a state of 1, which is already this one. So when I'm in S1 state, input of JK equals to 1, 0 occurs. I remain in the same state. Okay. So I'm done with that. And finally, with JK equal to 1, 1, I'm in S1 state, input of 1, 1 occurs. When I'm in this state, the next state, what should that be? How should I transition? Should I remain in the same state?
Would you transition out for that one?
I should transition to the next state, right? Or to the S0 state. Right? Because I toggle. My output in the next clock instance should toggle. So it should toggle from 1 to 0. When I'm in this state, 1, 1 occurs, I should toggle to 0. And if I keep the value, you can see this, right? If I keep the value of Jk equal to 1, 1. So now I'm in this state. I keep the value of Jk to be 1, 1. I again toggle back to this state, and that process repeats, consistent with what we have seen in the last class. So now that's the state diagram of a Jk flip-flop. Okay. Okay. So in this case, I have S0 encoded as 0, S1, let's say encoded as 1. Let's say my state variable here is A, because I have a single state variable. My S0 is encoded as 0, S1 is encoded as 1. Okay. Now what I would like to do is see if I can actually implement this as a state machine and see what I would get. Okay, I need to say, okay, we have time, yeah. All right, let's see how we can do that. All right, so I would like you guys to refer back to your, I hope you have drawn this in your notebook. So you should be able to refer back to that diagram. So now I'm going to erase that and put this information in the form of a table. Okay. So let's do that. So this is the state table. Now I'm drawing the state table. Okay. So the components of the table are these. So this is the exact format that you will be using every time you're doing the state table. So first you start with the present state. So that's the first column of your table. That is represented by your state variable A. In this case, we only have one state variable A. The next column is the input. Okay. In this case, I have two inputs, J and K. The next column would be the next state. Again, that is represented by A plus, which basically tells you what the next state would be. And the output. If you have any output, you can represent that here. But in this case, my output is nothing but the state, so I don't really have to explicitly state that here. Okay. All right. And now I look at all possible combinations between A, J, and K. So these are my present state, J, and K. I look at all possible combinations between A, J, and K. So let's look at that. So I start with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Any question here? Okay.
Yeah, I have a question.
Yeah, please go ahead.
Is the single present state A because we're only using one JK flip-flop with the output QT plus 1?
So for the example of a JK flip-flop, the way we have constituted the state was the output of that flip-flop Q, right? The state of being of Q itself was called the state. That's how we kind of came up with the state for the JK flip-flop. Because I have only one variable Q, which can only exist in 0 or 1 state, right? So the state variable, I only have two states, S0 and S1. So I can encode S0 as 0 state, S1 as 1 state. So S0, so I use a single state variable A, where I'm encoding S0 as 0 with a unique code 0, S1 as a state with a unique code 1. If I had 4 states, of course I need 2 state variables, but in this case I only have 2 states. I can simply encode them with a single binary bit. Does it make sense?
Yeah, it does. Thank you.
Okay, so now you refer back from your state diagram. Okay, so I'm in this state, S0 state, because that corresponds to S0 state, right? A equal to 0 corresponds to S0 state. A equal to 1 corresponds to S1 state. So I'm in the S0 state and an input of 0, 0 occurs. And from the state diagram, now you can read out, based on the transitions, if you recall, when I'm in S0 state and an input of 0, 0 occurs, or when I'm in the S0 state, my next state would be what? The same state, right? Is that right? If I'm in a 0 state, input of Jk equal to 0, 0 occurs, that takes me back to the same state. In other words, I remain in the same state, 0. Does that make sense?
Yes.
Now, if I'm in a 0 state, 0, 1 occurs. That's the reset state, so I remain in the same state, so that's also 0. If I'm in a 0 state, input of 1, 0 occurs, my next state would be 1, right? Because that's the set state. That's going to be 1. Again, that's S0, S0, S1, right? If I'm in a 0 state, input of 1, 1 occurs. That takes me to the next state as S1 again. Again, I don't have the state diagram here, but I'm hoping that you refer to the state diagram from your notes to populate this table. Okay, so all I'm looking at is the state diagram and trying to translate that state diagram information to the state table. So I'm in S1 state, input of Jk equal to 0, 0 occurs. Thus, I remain in the same state, which is the 1 state. I'm in S1 state, which is state variable of A equal to 1. Input of 0, 1 occurs. My state transition from the state diagram tells me that I go to the 0 state. I'm in S1 state, Jk of 1, 0 occurs. I remain in the same state. I'm in S1 state, input of 1, 1 occurs. That toggles me. I go to the next state. I go to the S0 state. Again, all this information is obtained from the state diagram. Okay, so your state diagram is important. You need to come up with the state diagram first, followed by the state table. State table is nothing but a more formal representation of your state diagram. There's nothing different. It's just the same thing, but it allows us to realize the circuit. Okay, now let's see how we can realize it. Okay, let me take a pause here and let me see if you have any questions here. Are you with me?
Yes.
Okay, now what do we have to do here? If you go back to your now this is where your block diagram actually comes very handy, because that tells you exactly what you have to do, right? Your block diagram, if you recall, was something like this. So you need to basically derive this combinational block, which takes in the inputs J and K. These are the inputs you have identified, J and K, along with the present state, which is A in this case. So it's combining the inputs along with the present state to give you what is the output, A plus, or the next state in this case, A plus, right? Where is this A plus going? This is basically going to a D flip-flop. Let's say this DA, QA. That's the clock for the flip-flop. And that's the generic state diagram, block diagram, right? So this is what you have to derive. And you have to design this block, this combinational block. This is what is needed. What you need to do here is A plus. How do I do this? Because ultimately you're designing this combinational block, I can use K-maps. So here I can use K-map. Let's say this should be a simple K-map. 8 input K-map or an 8 cell K-map between A, J and K, because those are the inputs to this combinational block. A, J and K, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and then the outputs, because I'm trying to do it for A plus, I'm trying to compute A plus. So here I have 0, 0, 1, 1, 1, 0, 1, 0. Is that right? 0, 0, 1, 1, 1, 0, 1, 0. Yeah. And then I would combine them. How do I combine them? So basically I can combine these, and then I can combine these two. Right? Again, I'm doing this for A plus. A plus is the output of this combinational block I'm trying to derive. Everything else is standard. This is a basic standard template, if you will. I'm trying to do this. So A plus is, so here I have A prime, 1, 1, 1, 0, so A prime J, or here I have A 0, 0, 1, 0, K prime, right? So that's the function. So now I know exactly how to get A plus as a function of J, K and A, right? So here, that's A prime J, A prime J plus A, I'm sorry, that's A prime J plus A K prime, and that gives me my A. Okay, oops, are you able to see that? There you go. So I have A prime J plus A K prime. Those are the two inputs, J and K, and A, the present input, to the combinational block. I derived my A plus as a function between A, J and K. This is what I got. Okay. And if you notice this, if you really go back to what we have done in the last class, where I just simply provided you with the combinational, with the diagram for the J-K flip-flop, you will see that this diagram what we've obtained through this exercise is exactly the same thing. If you compare these two, and that's something I would like you to do as a homework, if you can compare these two, that's exactly identical. Previously, in the last class, I just gave you that, but now we actually derived the J-K flip-flop through this state machine approach, where we go. So now it's a very generic approach. If you define your own flip-flop, a new flip-flop, kind of a flip-flop, to have some kind of a behavior, let's say, you should be able to do that. You should be able to design that through the state machine approach. So it's a very generic approach that you can apply to a design of any circuit, any state machine. Okay, I hope that makes sense. Let me see if you have any questions now. So with that, I'm going to post the final homework on Blackboard. You may not be able to do all the problems, but I will specify what problems you should attempt. Make sure you do them. Okay. And this is actually a very interesting topic. I hope you'll actually enjoy putting together all the concepts that you have learned and coming up with the design of some interesting circuits, state machines. Any questions, by the way? that I can, does that make sense? The approach makes sense. Okay, very good. All right, so again, if you practice some of the problems on the homework, I think that will reinforce your understanding. Okay. All right, so if you don't have any questions, this is where we stop.